Welcome. And so, the speakers have names for each of the sessions. And John doesn't like the fact that we name them. It's like the one right after lunch is the one that you're falling asleep. And, well, I won't give you all the names, but you just got some energy, so hopefully we're not going to all just pass out before dinner here. We're going to be talking about embedded today. My name is Michael Caisse, and I work for Ciere Consulting. We do a variety of different systems or programming for different systems, ranging from very small devices, 2K of RAM, no operating system, just a little microcontroller to do something on a board, all the way up to very large cloud distributed systems that are processing, tens of thousands of requests every minute and have many terabytes of data each day going in and out. And so we have a large span of things that we do, and it's a lot of different hats, and it's enjoyable. The last year, we've been doing a lot more work in embedded, and so I'm going to talk about that. I started working with smaller, what I think today would call smaller processors, back in the mid-'80s, and somewhere around 92 or so, decided that it'd be really fun to try to get that onto an RTOS, and it was not as much fun as I thought it would be initially. Things have moved on since then. This was the alternate name, the contemporary C++, because John and I really, have debates constantly about whether we should call things modern or not. And I think contemporary is really what we're talking about when we're talking about C++ today. Modern is a style, and we're talking about really, the compilers of today. And the only problem is it would not actually go through the program committee with that title, so we're going to actually use that as our working title throughout then the discussion. But now it's just between us. We know what the real title is. All right, so this is a continuation of the saga that began a talk that I gave earlier at CPP Now in May. It is not a prerequisite. It's just discussing some of the things and things that we found along the way. Now, what's interesting to me is that CPP Now is not the type of talk that really has embedded type stuff, yet I'd like you to notice the view count is huge for really a conference that's not about embedded. And I think that's indicative of people trying to get C++ or more modern idioms on smaller systems. Today, when we're talking about embedded inside of this particular discussion, I'm talking about it in realm of putting C++ on bare metal, so there's no operating system, and the amount of memory and whatnot. We'll talk about kind of a system that we're going to use as the standard for today. I want to make a public shout out to Xavier Thomas, who followed the instructions and marked where the important parts were in the previous video. I suspect some of you will do the same. So somewhere around, if we use this as a guide, I guess maybe about halfway through this talk, because that was a 90-minute talk, good stuff will happen. All right. So let's talk about the project. So this is based upon a project that we're doing for a client, this particular talk. And they are taking a hydraulic system and converting it into something that is basically brushless motor ran. So instead of what you normally have in a hydraulic system, you've got some big diesel motor that's spinning at a rate pretty much all the time the same rate. It's got a manifold that the oil gets pumped through. There's valves that kind of change the direction that things are going through the different whatevers that you want to control. In this case, we've got different hydraulic actuators and motors and whatnot. And then there's a cooling system. All of this creates some amount of inefficiency. And one of the things that they're working on is how to make this more efficient. Their system is something that looks like this, where each of the hydraulic things that need to be controlled are hooked up to what they call a hydropulse. And these are the brushless motor systems, and we're working on the controllers for those. That's enough actually probably about that. We'll run out of time. Here's an application, a standard application for something like this. This is a tree shaker. So these are farm equipment that are completely hydraulic driven. So they have a diesel engine merely to run the hydraulics. So the wheels turn through hydraulics, the extensions and actuators move through hydraulics. They grab a tree, they shake it so the nuts fall off. They've got little sweepers that spin around, collecting things. The whole thing is hydraulic, and in this particular case, in the Central Valley of California, where an enormous amount of produce and nuts and whatnot, for example, almonds, like 80% of all the almonds in the world are produced there. There's also a lot now of diesel emissions, and they're trying to figure out how to clean the air up. One way would be to use something like this. So you can kind of see what the application is. What we have from just a very high point of view, looking from very tall down, we have this MPU that is going to control a variety of different things. It's looking at a couple different analog to digital converters with various speeds and various things connected to them, near field communication chip that's on it, a variety of different memories, lots of different pressure sensors. There's an FPGA that we're responsible for doing some work with, an encoder, and then there's some different communication ways to talk to it, CAN bus and EtherCAT and different ways to talk to this thing. And all of it needs to be controlled by the MPU. An MPU is really, just think of it as like an MCU, but it doesn't have memory on board. This is a diagram to give you an idea of what the processor is that we're dealing with. It is a Renesas processor. The processor itself, or the chip itself, actually has two processors in it. It has an R4, which is ARM, has 3 classes. That's where the ARM comes from. A class processors are application-based. R-based are real-time based. It means that they have a different interrupt controller that does not do vectorized additional jumps. The M and then M for mobile low power. This particular processor or chip has actually an R class and an M class in it. And that actually ends up becoming a small problem for us because the vendor would like to use the M class processor without you touching it to handle all kinds of communication things like the EtherCAT or CAN bus and whatnot, encoder. And then you write your application on the R class. The problem is that somehow they're both in there and you need to work with them, and the tool sets make it very complicated to do that. This is kind of looking inside of the processor. The important part for us to look at right now is that we've got this Cortex R4, and it has these things called TCM. This is just basically what's called tightly coupled memory. It's memory that's directly attached to the processor. You know, if you're dealing with things that are larger, you might think about them as like cache in essence, but as you can see, it doesn't really go off somewhere else. The tightly coupled memory is what's going to get loaded up. Program's going to run out of it and whatnot. The M3 processor is way up here, and it has what you would normally expect, a bunch of bus architecture that it needs to go through in order to do any work. This application, in addition to a variety of communication bits and pieces that it has to do and management of, whatnot, it has a spinning motor, and as this motor is spinning around, it has to do some acquisition, it has to do some processing, and then it has to do some adjustment to something else, right? And as the motor spins, it can't miss the time, so it's a hard real-time system because if it misses the time, everything just kind of falls apart, right? So this is what we're working in. There is no operating system on this. And the question, of course, is like, why in the world would you want to use C++ on this? Like, what's the point? And the first point on why you'd want to use C++ is because you submit a talk about using C++ on an embedded system, and as a result, you now need a project with C++ on it. But the reality is, C++ actually provides a variety of different abstractions that are useful. Those abstractions allow us to write better code faster, code that we actually can feel confident about because we're going to assemble it in such a way that if it compiles, our confidence goes up. So it's correct by assembly, and we're going to use the type system to help us out. That's really key to why, at least personally, why I like to use C++ on projects that are very small processors. It gives me a certain amount of confidence that the system is correct. The Saga continuing, the original Saga, that episode contained all kinds of interesting things like vendor tools from the vendor itself pointing to domains that were no longer actually owned by the vendor, fun and games with tech support. which included phrases like, why in the world are you using C++? Please don't do that anymore. And you know, the good, bad, and ugly that comes from Twitter and Reddit. It also included a whole lot of information about Michael basically giving up at some point and realizing that the problem was going to be complicated and hard, and giving it to somebody who's like very senior named Sharon, who had 30 years of experience. And Sharon happens to be in the audience today. So all that stuff I said about Sharon previously and just like sloughing work off to her, we won't talk about today, okay? Because then she'll know about it, because I'm sure she hasn't watched that video previously. It even had clickbait. Oh, it was wonderful. But what I want us to think about, one thing that we took away from it was IDEs that we get from vendors who are selling chips, basically. They're there for one purpose. It's time to hello world. How fast can I show you something that works on a dev board? Because then I can sell the chip to you. It appears to work well and it appears to work easily. Unfortunately, time to hello world doesn't help us with a lot of things. It has some good things to it, which is we can actually get a dev board up and running and analyze whether or not the chip does what we want it to do. It has usually built-in target type information in it, or excuse me, facilities in it, so we can easily hook up to the processor and upload whatever it is, despite however complicated it needs to be. It has, you know, the linker scripts come with it. Everything just kind of works for that first level. And debugging is typically built in without a hassle, so that's kind of nice. The bad side of it is that it's really geared towards single user development. And if you have a team of people working on a project, which I think most often we have a team of people working on projects, then it's very complicated to use what we would consider typical best practices. Best practices kind of start falling apart when you have an IDE that really restricts the amount of things that you can do and expects all the files to be in a certain spot on your personal machine, right? And so that doesn't really work well. It's hard to integrate with the team. Hard to integrate then obviously also with some type of a CI. And it also hides a fair amount of magic. And the magic part is actually very interesting because typically embedded developers don't like magic hidden, which is why they don't like C++. But when there are tools doing it, it seems like it's okay. And what I mean by magic, as an example, is we have the R4 processor, but we also had that Cortex M3 processor. And who knows how the code is generated for the M3? It's like black magic. You just kind of like click this button, open this thing, turn that panel on, turn these little drivers on. The next thing you know, somehow it has code on it and it's running. I don't know where it came from or where it went. Unfortunately, of course, those are the things you have to tease out if you want to move to a system that has the whole CI and CD and the different parts that you want for well-controlled software. Now, I received actually a fair number of emails from people after my first talk. In fact, I received one just a couple of weeks ago, followed up with a phone call, and the individual said, you know, my team is kind of split at the moment. Half of the team says, yeah, see how hard it is? Why in the world should we do it? And the other half of the team is saying, hey, somebody else did it. So lots of people do this and work through it. And I'm hoping that you all will come away with thinking that it's actually worth the extra work. My experience is that, yes, it is extra work to get going. Time to hello world stinks. It's really horrible. But once you get past that, your ability to actually iterate and produce quality product after that is really high. All right, so we wanted basic tools. We wanted actually the GNU tool set just from ARM's website. We didn't want any special weird thing from the vendor, the chip vendor. CMake wasn't a necessary thing, but it would have been interesting to see if we could get CMake working. We got CMake working. We wanted normal static analysis. We wanted all the normal analyzer tools. We wanted to use a continuous integration system and a continuous deployment system. So what did we do to get this all to work? Well, it ends up that we have a heterogeneous system at work. I guess that's my fault because I let anybody buy whatever computer they want to do their development. And as an example, Sharon has a Windows machine. I have a Mac. The build server is Linux, and then we've got some Linux machines running around the office. We've got a bunch of build machines that are in the cloud. And so like nothing is the same. And it would be really nice to have the same tools running on everything. And supposedly this is what Docker was built for. Now, you can watch lots of talks about how to get Docker running and whatnot. But I want to mention this as a tool that is super useful if you're doing a lot of embedded work or work where you have a tool set that is important for your team to continue using over and over again. One way that people use Docker, unfortunately, is to have all the data and files copied into the image, and then it does some work, and then it copies the good stuff back out. Don't do that. Just find DotCross. Go online, find DotCross. It's in GitHub. It's kind of the base to start. Now, DotCross for us would not work because we have bare metal. We're not interested in an OS for the target, but it can be a base layer. And the nice thing about DotCross is it allows you to use whatever your normal tools are on your system. You're modifying files inside of your file system. You're using Git. You're using whatever happens to be for your favorite editor. And then when you invoke the command, what you end up getting is like there's an additional launch, and it's using the files that are on your file system. It's leaving them there in your file system. So that's kind of nice. And it creates a repeatable environment for us. How many of you have ever had this problem where you have got cross compilers on multiple machines and they don't seem to produce the same result? Okay, now the rest of you that are lying, you can raise your hand if you want, but I guess you don't have to. No, it sometimes is fairly hard to keep especially heterogeneous environments in sync with the tools, and we're finding that this is working well for us. So in theory, DotCross, you can find it on GitHub. This is the part of where we do a demo and we hope it works, right? So against my better judgment, in theory what happens is, okay, so we don't have, this is a project that's set up with this thing. There is no build directory or anything. So let's go ahead and, not that. Okay, so here is how you would run this with this DotCross environment. It creates kind of a launcher, and then you just give the commands that you would normally give at that point on, and it supports all kinds of different Unixy commands, and then installing new ones is pretty straightforward. So we're going to go ahead and just like run CMake, and bam, it creates some stuff. And so now we can see like we have our normal build directory with CMake CRUD in it. And now if I wanted to make it, I could just say, and now it's building using the tools that are inside the Docker image and leaving the files local. And so that's kind of that's a nice setup. We have clients who do a variety of different things using Docker, and the ones that don't use DotCross, it's kind of like the stuff still exists inside of the Docker image, and you kind of have to pull it out sometimes if you want. And there's like crazy other ways to do it. People have gone through some good work to get this working. All right. So this is where the cameraman hates me. I don't really mean to be running off stage because I just forgot about it. So this type of setup is really convenient. In fact, that won't be loud. So this is a little FPGA. The specs are up behind me, and this is a board called a Tiny FPGA. Luke does these. It's an open hardware project, and it's not very interesting. You may or may not be able to see the little LED blinking, but what's happening is I've set up one of these DockerCross things that takes and it's Clifford Wolf's RISC-V core is being built, and there's a C program that's also being compiled and loaded onto here, and the whole thing's just kind of running, right? So this is basically like a softcore, right, on an FPGA, and all that's just kind of set up with whatever. And this is all using all open source tools. Icestorm is an open source FPGA setup too. All right, so we've got our standard tools. And once you have your tools, you have to solve a whole bunch of different problems, right? You have to figure out what happens when you reset the chip. How do you get that working? What are the memory layouts? What are the different startup needs of any particular device? Peripheral needs. And then, there are different languages that are appropriate for these different things. When you're first starting something up, you probably have written your code in assembly, right? So you write your boot code in assembly, some amount of it, until you get tired of that, and you want a slightly higher abstraction. So you write just enough in assembly, and then you switch over into C. And you write the rest of your bootloader in C. And a lot of people kind of stop there. Their application is also then written in C. And this particular device, how it boots up, the bootloader is loaded inside of this tightly coupled memory, the second one, B1, which will later be used as actually the stack for the application. It's loaded into there, and then the bootloader runs, and it loads inside the application into the A tightly coupled memory. The thing that I want to be able to do is, yes, I have to write assembly to get the silly thing working, and I have to write some amount of C. I guess I could write it all in assembly, but I prefer to write it in C for the rest of the bootloader. But boy, I sure want my application running in C++. I want to move one more layer up. Jason Turner was on a podcast a couple months ago for Embedded FM, and one of the blog posts on there is this, which is switching from assembly to C. So that whole idea of wanting to actually create abstractions and move further up, it exists everywhere. It's just how far people want to go. This is actually a pretty good podcast. If you'd like to listen to it, it was insightful and it reminded me a lot of the struggle that people have and just understanding why C++ might be useful on a small device. So I think people want to go further, and they want abstractions that are higher. It's just that I want to go further than stopping at C. So let's talk about some C++ things. Things that are important. So zero cost abstractions are important. Zero cost abstractions generally are also scary for some people, but they're important. Host debugging is important to me. Correctness, and that's going to be through types for us. And again, this idea of abstractions, but slightly different that we're going to look at. So first I want to talk about just the idea of wanting your code to become more declarative in nature. You want to get to this place where you've begun to move the things that are low level, belong down in the guts. They're the stuff that's just hardware specific things. You want to move that down as far as possible, and you want to move the value up. Now, when I say that, it sounds obvious, but when you look at standard embedded C code, that's not what happens. It's like, hey, I just need to twiddle a bit. Just this one right here. And it doesn't really matter where you are in your code stack. Twiddling a bit is just like ORing something over here or ANDing something inside some memory register, and you just do it. And the next thing you know, you have like no abstractions. You have no layers at all. Why? Because it's expensive to create layers in C. That's why. It's not that people don't want to, it just has a cost associated with it. And so one of the nice things about C++ is we remove the cost of the abstractions. We end up with something that's low cost. This is a talk you should watch. It talks a lot about how to actually create better abstractions. So watch this. This is a great talk. It works for embedded just as well as it works for all kinds of other things, talking about declarative. Do you like the talk, Ben? oh my goodness, Ben liked the talk so much, he's talking about it again on Friday here. So you have a chance to see it. Good job. All right, so what is a zero-cost abstraction? All right, we've got this piece of code. The main is going to take in really a list of things from the user. The user is going to be able to put a bunch of numbers on the input, and it's just going to count up how many number 8s are on the input. Okay, that's all it's going to do. So we're going to call this thing called count value. We're going to pass in the range and the thing that we're searching for. We're searching for the number 8. The code looks like this. It's a very simple version of it. We've got this for loop while length. It's going through, looking at a to I of the value. It's comparing it to what was passed in. It's incrementing it and returns the value. Pretty straightforward. Nothing surprising there. Now, this is what it's going to create for the code. You can kind of just ignore the assembly. We're not going to dig into it. But what we're going to notice is we've got, first of all, it looks like it's been inlined. So the routine itself shows up in main, and then, hey, the routine still also shows up. So one thing that we can take away from this is when we see stuff like this, for our small embedded things, we want to make sure that link time optimization is turned on. LTO is going to help us with producing smaller sizes in the binaries. This is information we can't decide until link time. And LTO is something you have to turn in both at the compiler and the linker. It needs information from both bits in order to get the whole thing to work. Turn that on, this would go away. Now the other thing is we could just say, hey, this is local. Nothing else is going to ever call this. And we could actually just say, hey, namespace is the anonymous namespace, and now the compiler realizes that if it's not called locally, it's not used locally, it can't be used externally, and that would fall away if we wanted to do that. So another takeaway from this is if we actually think about the namespaces of things, if things are local, we use namespacing, anonymous namespaces to do that, we actually will just kind of end up with a better set of code going into the linker.
If you had labeled it inline, would you get the same effect in all cases?
So the question is, if I labeled it inline, would I get the same effect in all cases? No, not in all cases. Yeah. All right, so does that code bother anybody other than this person over here? Does it bother anyone else other than Marshall? Yeah, okay, there are a few people. What does it bother you? Why does this bother you?
You could use an algorithm.
I could use an algorithm. Okay, now, I'm an embedded programmer who's been doing this for a while, and algorithms kind of worry me. I don't know. It just seems like here, I look at it, and it's really obvious what it does, right? I mean, that's the whole idea, right? It's not obvious what it does. That's why we want to use algorithms. So let's go ahead and use an algorithm. We have one. It's called COUNTIF. How nice, right? So let's just use the COUNTIF algorithm, and the predicate will just go ahead and see if the thing passed in is 8. Sound good enough? All right, now, what would we expect the compiler to do with this? Not the peanut gallery. So people who work on compilers, you can't talk. This is what we would expect. And the raw loop and the algorithm basically produce the same output. There are some minor differences, but for all practical purposes, it's basically the same output. That is not intuitive to most embedded programmers who are coming from C and going into C++. The first thing to realize is that the abstractions have zero cost. We can talk about things at a much higher level. We can talk about things by saying COUNTIF. When I say COUNTIF, I know what it's going to do. I don't have to analyze the loop. And by providing information not just to the compiler, but to one another about what in the world this thing is, it's so much easier to maintain and understand your code. We can think at a higher level. So we want to get to that point. Now we've kind of just changed it slightly. I'm using a capture now. So the idea is that we're capturing with 8, and there's really no reason to use the capture to capture 8, except just to demonstrate that the compiler does the same thing. It's not like by adding captures and whatnot, the compiler's not smart enough to make that go away for me. I can actually use the language fully and get a good result from it. All right. So let's, instead of taking the input from the command line, let's just have some data in the system. Now, we'll let you look at it for a moment. I'd like to thank Jens, who pointed out in the YouTube comments that there was an error on this slide. It's very embarrassing. Does anybody see the error? My size of. You know why this is so embarrassing? It's because I wrote begin and end originally when I gave this slide. And I thought, I'm going to make it friendlier by removing begin and end so that there aren't so many things on it that somebody coming maybe from C would not be comfortable with. And in doing that, I created like just a bonehead error, right? I'm off. Not by one, by a lot. So let's not do it that way. Let's use begin and end. So begin and end, that's really how we should actually talk about the begin and the end of ranges. In something just so incredibly simple, in which I probably was trying pretty hard not to make mistakes, I made a mistake. One in which, by the way, all the slides worked out fine. These things compile. It gave me results that seemed reasonable. You know, this would have been great until it shipped and something bad happened, because that's when bad things happen. By having a language in which we can talk about ideas at a higher level and get good and correct results, that's a good thing. And you know, that wasn't even planned. That was just like, made a mistake, begin and end, that's what we should have used. All right, so we shove this in, what do we get? All right, so this has been compiled with OS. That's the other thing. With embedded things, you typically are compiling for size. That's what you're interested in. And so we've got some amount of assembly on the left, and we have on the right, what is this? Yeah, the data. Now, when I look at this, it seems like it shouldn't be too hard to count them. So why is it hard to count them? Yeah, they're not const. They may change, but you know the importance of const. If we add const in, because const is important, then I end up with this. That's the 2 lines at the bottom, right? So return 2. So we've got 2. The other thing we want to take away is abstractions not only don't have additional overhead, but if we use const appropriately, we end up with big gains, like really large gains. We can still put the data inside of the code like we want to, but it's going to calculate it. The compiler is going to calculate the outcome for us. We're going to end up with something nice. All right. So let's talk about polymorphism for a moment. What is polymorphism?
The same code does something different depending on some condition.
Okay, same code does something different depending upon condition. We're going to say, for me at least at the moment, that a base class is able to use the behavior of a derived class as the derived classes change about, right? So it's easier the other way around, right? A derived class using the behavior of the base class, that's very natural. But for a base class to be able to utilize the behaviors of derived classes as the derived class changes, something has to happen there. And typically, what happens there is we write things like virtual. So we're going to have this main. It's simply going to go through and iterate, calling getPoint. As it passes in one value, it's going to get the other value out as if it's passing in an X and getting a Y. Let's just say it's going to inherit from something called curve. And we're going to have a simple version, which does nothing more. We're going to look at the base class here of curve. It has a virtual that calls getPoint, or excuse me, a virtual function called getPoint, and it's going to call adjust. And adjust is a virtual method that the derived type will implement. So the behavior, the algorithm bit, we stick inside the base. But it needs information from the derived type. And so therefore, we make it virtual. Why? Because there's going to be a vtable for us. The vtable provides this level of indirection so that when it calls adjust, it looks and says, oh, where do I need to call that? And there's some jump table to call the correct version of the derived type. So, so that's our very simple. Now, it produces some code. Quite a bit of code, in fact. And some of it is obvious when we start looking. We're going to see some RTTI, some runtime types. We're going to see some jump codes that are inside there. Some indirection from the virtual tables are happening over and over again. That's what the offsets are. We've got a lot of code for a small bit of task. Virtual things are horrible in embedded systems for a whole lot of reasons. Typically, you don't want the additional indirection, but more importantly, you don't want all the overhead of the cruft that just comes in along the way. Well, what's interesting to me mostly about polymorphism is seldom do we really need runtime polymorphism. Most of the time, what we care about is this behavior that changes on the derived type, and we know what it's going to be. We know the derived type. We've just put the algorithms into the base. And so we really just need compile time. So same thing, compile time though looks like this. And you've probably seen this pattern before. It's a curiously recurring template pattern, CRTP, because we're really bad at naming things. One of the things we're not good at as an industry. So the CRT pattern looks like this, where we've got, where we're deriving from something, and the template parameter is the name of the thing that we're creating. So class simple is deriving from curve and it's passing in simple. CRTP is used for two things. Either it's used for compile time polymorphism, or it's using for injecting behavior. If you've ever used enable shared from this, it's injecting behavior. That's what you're trying to do there. All right, so how do we use it? Here's our base class that we had before. It has a template parameter, of course, because we're going to be passing that on in. And how should we use that? Well, like this. We're going to say, instead of just calling adjust, now we're going to say the impl adjust. Now there's different ways to do this. I end up using impl a lot. Sometimes people use derived. It has more letters. I don't know. What is impl? Impl is nothing more than casting to casting the this pointer to the derived type. And that's safe to do because it knows what type it is, right? That's how it was instantiated. It was instantiated with the type. So you're able to put the algorithm in there. Now, what do we end up with? Well, we end up with a much smaller piece of code, and we still end up with polymorphism. We still end up with a technique that we want, but the code is smaller.
I agree with everything you did there, because you actually had an extra bloat in the previous C++. You had a virtual function that didn't need to be virtual.
All right, don't ruin my next slides. I'm not going to repeat it because he's going to try to ruin my slide coming up. Stop. All right, so devirtualization. So it ends up that the compiler, it was really hard to make it create all that bloat for me in that first couple slides because it wanted to devirtualize this. It knew that it wasn't needed in a virtualized manner. The compiler actually produced the same code from all the work that I had gone through. Devirtualization, though, can fall apart as soon as a couple levels get confused or a variety of other things. So, you know, if you're needing to depend upon the fact that this happens, you probably shouldn't. But yeah, CRTP and the devirtualized version are basically the same. Okay, so a couple things that we take away. Inline functions don't look like the code that we wrote. This can be scary. You know, this could be one of those things where I wrote some code, I expected it to do something, and it didn't do it. In fact, this is one of the arguments of why not to use C++. Is because it inlines and it changes things and optimizes things, and I don't really know what the code does anymore. Const can allow the compiler to optimize a variety of line of codes away for us. Static polymorphism, it's good. And the results, they can change with different debug and optimization flags. Our results can change. Now, one thing at this point is we can say debugging might be hard. Have you ever met anybody, in fact, maybe it's you, who's like, debugging C++ is crazy. As soon as I turn the debugger on and I start stepping through, I have no idea where I'm going to ever be. So this is what Countif looks like under the hood, right? And I don't know, you could talk to, we have lots of implementers around this week. You can talk to them why they can't just come up with names that make sense, but they've got lots of decorations and they're long and they're crazy. Eventually we get to that, and oh yeah, there's that other concept requirement stuff there, and it can look noisy if you're stepping into it. First of all, I'd say don't step into algorithms, because that's probably not what's wrong. So what does this look like without optimizations turned on? Well, it's that, and that, and that, and that, and yeah, okay, so and that too. I don't think actually I want this code, right? I want the optimizer to do its job. That's what I want. So challenges, we want to think about this. There's going to be some challenges in writing and debugging this thing. And so often what happens in the embedded world is -0. Why? Because if you do the man page and you look up -0, this is what it says. Reduce compilation time. That looks great. And make debugging produce the expected result. Two good things, right? Except that I really don't want those things. But this is why -0 is used a lot. All right, let's just take a look for a moment at some C code. We could be critical of the C code, but we're not going to at the moment, okay? It's going to serve an illustration for us. So, very simple piece of code. We're going to pass some values in. We're hoping that they get ordered, and we have a 32-bit value out. This is what we get. So, this is Compiler Explorer, godbolt.org is where you can find this. On the left-hand side, we've got the source. On the right-hand side, we have the assembly that came out. And this is the assembly produced with 0. It appears to be doing a lot of work for what I've asked it to do. And it's actually doing what -0 said it would do. All the things you expect. And if you think about it, what do I expect? Right? I've got a stack, and I've got registers that have to get pushed, and later they're going to have to get popped. And there's a lot of work that's going to occur to call a function, right? So now if I turned on optimization, what would happen? Something else. It doesn't have to worry about that. Why? Because it knows what's inside of the registers and what it's going to return. I get something quite a bit more simple. In fact, it might even look efficient at the moment, right? That doesn't look so bad. But if I was a C programmer, that's not what I would do. I would create a macro that's going to do this for me. Why? Because somehow that's less scary to create an inline with a macro. Can anybody tell me why would an inline with a macro be scary, maybe? Why are macros? Okay, they might be scary because they're not type safe suddenly. There's no type information about a macro, right? So while I'm going to get maybe this concept of like inlining, and it'll feel less scary, just let the compiler do its job. So here I'm just trying to actually call it from what we had before, and we can see that it's like the same junk that we had before. We turn the optimizer on, we can see that it's small again. In fact, probably wouldn't really do it that way if I was a C programmer. I'd just call the macro directly, right? Okay, and that's not so bad there then. Yeah.
Go back 2 slides. Please.
Oh, only if there's no error will I go back.
No. Forward one. So if you make the function static, it'll all just go away when you go up to 2 instructions.
True, I could make the function static. Yeah.
And then you'd be there.
Yep, and then we'd eventually be here. And that gets me what I wanted. Now, it gets me what I wanted, but it almost, to me, looks like not what I had really desired. As we look through the different iterations, like this one, I don't know what it's doing, but there's some additional stuff in there that surprises me. And while on one side I say I have -0 and I'm going to expect what I want, that's not what I want. I don't really want O0 because O0 is not going to actually get me the benefit that I want. And so I start making macros in order to get inlines. And I start actually doing all these other things to get what I really want. And what I really want is probably just to call a function and turn the optimizer on. That's probably what I want. And the reason is, at the end of the day, I can't actually guess what the compiler might be doing. Nobody can really pretend that they know what the compiler is doing by the end of the day. You're just guessing, right? And so what you have to do is measure and test. In fact, you always have to measure and test. If you think you can write software in such a way that you can just like noodle out what the compiler is going to do and what the assembly looks like, you're kind of like fooling yourself. So instead, just turn the optimizer on and measure and test, which is what you have to do actually anyhow if you don't do that. So the other thing is, we'll move on. So the idea that that we seem to be getting into this mode of operation in which we write software, and as soon as I'm done writing it, I want to run it in the debugger to see if it works right. If you turn your debugger on, you have a problem. And I don't mean the code has a problem. I mean you have a problem. You shouldn't be turning your debugger on immediately to figure out what your code's doing. Like, noodle through it. Think about it. Try to figure out and reason, what did I write? What's the answer supposed to be? How is this supposed to work? There are situations, obviously, where we turn debuggers on, but it's not supposed to be the tool that we're constantly going to. It ends up with really bad code that we write, and we don't actually understand the problem anymore. So one thing, you don't step into COUNTIF to see how COUNTIF's working. You just, like, COUNTIF does what it's supposed to do. And if you've got a problem, you kind of like think about what the problem is, and maybe you're instrumenting at some point if it's pretty bad, but running to the debugger all the time, it's not a great plan. So let's talk about the value versus the hardware-specific things. Value are things like algorithms, business stuff. That particular thing that we had that we were talking about earlier, the motor controller, it uses some mathematical algorithm to determine and detect where it's going to be coming up. It measures a bunch of information about current coming from phases so that it can determine where the next iteration of the coils needs to be. That is all business logic. I can test that and know that the algorithm is rock solid, not on hardware. But the only way I can do that is if I actually write my code in such a way where I've separated the value up and the hardware bits down. So the other thing that I achieve by doing that isn't just this idea of layering and making me happy about abstractions. The abstractions allow me to have a better tested system. So sometimes what happens here is we do this because we're uncomfortable with knowing what's going to be executed. Here's some idiomatic C code. And if you have written C code or in the embedded world doing that, this is a typical way to solve a particular problem. In fact, it's really the right way to solve this problem. Now, if you're a C++ programmer, you look at this and say, we have a different way to solve this problem. We have constructors and destructors that take care of cleanup at the proper time for us. This is very manual. But if you're coming from a world in which you believe that the compiler is the evil thing in the back always trying to harm you, then you're worried constantly what's going to be executed, and then when is it going to be executed? When will there be instructions put in? What is the compiler doing now? It's actually not that hard, right? Constructors construct, destructors destruct. If you don't write any code in them, it's not doing anything. So it looks like a struct, basically, right? So this is error prone. Anybody have code like this that there was ever an error in? Okay, anybody have code like this that there wasn't an error in? Exactly, nobody, right? Because this is just hard to do right. And so the idiomatic way to write C++ code is with constructors and destructors. Some of the other things that come out is that there's like this, I think it was artisanal, was the comment that was made, way to write. When I look at C++ code, it looks so sophisticated. There's nothing sophisticated about it, right? They're just different idioms. And so you need to get used to the idioms. And one of the questions that has arisen quite a bit over the last few weeks was, how do I learn these idioms? And I think the best way to learn the idioms is not Stack Overflow, people. So the best way to probably learn the idioms is finding like a blog post of somebody who blogs well and knows this stuff, watching some YouTube videos. Jason Turner has a weekly video that talks about all kinds of different things and different idioms, different techniques, things that he's learned, as well as he's got these great blog posts. There's lots of people who do these things. All right, correctness. Type system needs to enforce correctness, and we want to move as much into compile time. So the good of separating is that we're going to be able to do that. And the bad is that, well, some people say that the bad is that we're too far removed, but there's really not a bad, so I'll just cross it out now. All right, so one of the things that we have to talk to is an FPGA, and we do that through a SPI bus. And the SPI bus has what's called master in, slave out, slave in, master in, yeah, that. Master in, slave out, and the other one, master out, slave in. So it's just this like ring that goes around, and the master side is producing clocks, and as clocks are going, it's just clocking in through a register and then clocking back out the other side. This is some code that exists in a project that has had a bunch of things changed. We readopted this. It was talking to a motor controller, a different motor controller, using a SPI bus. And this is what the code looked like, the C code. Now the problem is that if we needed to add more commands, which we needed to add a whole bunch more commands, we had to go and write something like this again. So there's some code that's doing some very low-level things. There's really no abstraction at all. The abstraction is the name of the method that I'm calling, and then at that point, I'm just kind of like banging bits, right? There's some lower-level parts that are actually sending the bits out for the stream. But let me ask, do you see anything with, maybe this here that might cause some problems? Yeah. We might swap them, right? By mistake. In fact, actually, somebody had swapped these by mistake, and it wasn't nice. Those two values to the motor controller meant something pretty important, and the result was actually, we broke something. So swapping things and getting mechanical stuff to break at the end isn't the result you want, right? You want your compile to break. So how would we solve that? Types. Yeah, we would actually have a type. We would know that by construction, the thing we were calling actually called the right thing and did the right stuff. So we replaced it with something that looks more like this. We have a protocol that's described by a series of classes. They have unique types. They are, and those types are built up with other types, right? It's very type-driven. And as a result, there's some other magic that happens. The magic is we just adapt the struct so that we can understand its type later on. We can then just use it, though. And by using it, I mean we can just call, for example, send message and send a type. And it knows how to serialize the type out the stream. The advantage of this is now we become more declarative. If I want to add a new message, I literally just make a new struct and I adapt it. I don't do anything else. It's pretty easy to do. I'm probably not going to make any mistakes, even me. I probably won't make any mistakes doing that. So it's extensible. It's also far fewer lines of code. It also compiled down to quite a bit less code in the end, the actual code itself. So this was a better way to go about solving the problem. State machines exist everywhere. Don't be afraid of state machines. Use and embrace state machines. So here's a state machine. It's written like UML diagram. this is using Chris Jusiak's state machine library. How many heard Chris earlier today speak? Yeah, great library. So we won't go over this a whole lot. You can see it online. But the idea is that we're using a domain-specific embedded language, and the thing at the top is the state machine, and it has things in it like states that have names, and it says things like this is the event and slash this is going to be the action that's going to take. Here, this is a guard. This is all a notation that exists, and that notation matches what goes inside the table. The machine table that I'm writing in code looks like the diagram. I'm probably not going to mess these up. I'll understand it when I go and look at it. It's not a bunch of switch statements. I have to believe it's going to do the right thing, and that might be a little scary, but you know what? I can test that to make sure it didn't mess up along the way. What does it produce? And here's the other thing, I guess. Nope. The other thing is, how do we use it? We use it by actually just calling on the machine process event, and we pass in a type. Well, that's interesting because I've already moved my stuff into types. What am I getting off my SPI bus? What am I getting off, in fact, off all of my communication devices on the CPU or the NPU? Types. How do I drive my state machine? With types. I just shove them in. I get types back out later. I shove those out. Communication things. I'm thinking at a much higher level, and the type system will actually tell me if I've constructed it properly or not. So a naive implementation takes 3 bytes of data of what we saw before, the enum1 and sml1. That's going to compile down to something that's the same as if I hand-coded it. That's pretty impressive. Internally, we use something called Laudin. It tries to move us up 1 level higher. So now I have this 1 level higher of abstraction in which a port describes some things that's going to be able to be communicated across the port. So it's a protocol. The protocol has in messages and out messages that it can receive. And when I hook those things up, like this picture here, they're hooked up. These are state machines that appear to be distributed. When I hook them up, I can check to make sure that the in and out messages at compile time are going to actually be compatible with one another. They're going to do the right thing. I'm not going to receive something that I don't understand what to do with. And I simply describe that like this. This is the protocol that I'm going to be speaking, and ports, again, are just types. So using the type system to help me out, I'm able to then tell at compile time that the thing is assembled properly and correctly. I'm not going to pass the wrong data to something and have a bad result. Some other abstractions you can look at online. Odin has quite a few different things that he talks about with the special function registers. Everything inside of an MPU looks like memory. And how to deal with that in such a way that makes sense. There's a lot of work that you can look online on better ways to think about it and do it that are, again, abstracted through types and at a higher level. Watch Odin's Mixin talk from 2018, CPP Now. Here's some features that like right off the bat you can get going with and not have any problems. Lambda expressions, algorithms, range-based for loop, move semantics are awesome, fold expressions are great, and initializer list, believe it or not, the thing that I like, if some of you, I recognize the faces, you were in my pre-conference class where I was bagging on initializer list. This is a great place for initializer list because there's so many places where we have constant lists of things that we need to actually pass around and initialize things with. So it's a good place to know what the begin and end of something are. Some final thoughts. Tool vendors aren't friendly. They don't want you to use C++. Sometimes they'll just actually say that. Poor Sharon, she found like this back door to get the C++ stuff to compile. And then she called and had a bug or two, and they said, you should upgrade to the next version, which had removed the back door. So it's just the way the environment is. But it's actually worth it to get past that. It's going to take some amount of time of fighting to get past your tool setup. But after that, the project runs smoothly, and you're able to actually put things together that you know are going to work. Use good tools. You can't use good tools if you're stuck with the vendor tools. That's just the way it is. You need to break out of that and use like all the normal things that we know that are good practices. Compiler Explorer is wonderful, measure, and then test. Thank you for your attention. If you have any questions, I think we're out of time, but I'm happy to take them afterwards. Yeah.
One of the problems in embedded is that you actually don't even have a standard library in many cases. What do you do about that?
Yeah, so the comment is one of the problems in embedded is that you don't have a standard library. Well, that's not entirely true. You have certain amounts of a standard library that will work, which is why I've been talking about the algorithms. Almost entirely all the algorithms are usable. And they work with things that understand ranges, begins and ends of things. We can write types that work fine with all the algorithms and raise ourselves up out of the for loop disaster.
Definitely the vendor is not going to provide you a standard library.
It just ships with the ARM compiler. You don't have to get a standard library from a. Pardon me? AVRs are supported by GNU tools. You can use, again, you can just use standard GNU tools to do this. You're right, if you use the vendor tool, you're severely restricted. But you don't need to use the vendor tool. There are things in the vendor tool that you want to steal, like linker scripts. And that's a good starting point, right? They have startup code. Just start with their startup code. Fix it so that it works with static types for constructors and destructors. Oh, I'm sorry, we have a mic. You'll have to run to the mic, sir.
Hi, great talk. I have a question regarding the vendor tools that you mentioned that, well, vendors generally don't want you to use C++. The problem that I've seen, I've been stumbling over and over again on is that embedded systems typically have designated memory areas, like read-only memory and, static RAM that you can use, but static RAM is, it's always too small, right?
Yeah.
And what I learned the hard way is unless you control where your program is landing, your algorithms more often than not start landing in a static RAM, which, of course, they should be landing in read-only memory, but the question here is how do you control where segments of your program land? How can you influence this, or how frequently did you end up modifying the library, the standard library that is shipped with your toolchain?
Okay, good question. So you really need to take ownership of a linker script and of the startup code when you get going, because all the magic startup code, right, and the linker script are really fine-tuned for not C++. And you're going to do things like turn exceptions off. Great, I've recovered all of those portions of those sections, right, inside of the linker script. But you're going to know where everything is. For this particular device, it's a 2,600-page manual, right, in order to know what all the registers and whatnot and memory maps are. But you're going to spend a lot of time in that to know where things are. And then the other half is, analysis of the output by looking at a map file or having a tool that looks at the map file. You'll know whether or not you're going to run into things you should not be running into.
So the follow-up question here is, this generally means the moment that you start using, for example, std vector, you end up modifying like 3/4 of the standard library because, generally you have to annotate everything or you have to tell linker script somehow where you want the pieces of the STL to land.
Yep. So I left this talk at bare metal. We don't actually use std vector. In fact, we don't use anything that requires allocations because we don't have an allocator. We don't write an allocator for it. And we don't use a library that has a pretend allocator either. So all the initialization happens at the beginning where we grab static bits of pool and we create our own pool memory or whatnot. But we're not allocating memory anywhere else. So we don't use vector. Yeah, we basically use an array, like std array, but std array, depending upon the library, has its own problems.
So as a comment to this question earlier about using algorithms, we found several bugs in algorithms delivered by the standard implementation of tool companies, like for smaller tooling companies or companies that make tooling for their own CPUs.
Okay.
So if you do use the native, maybe add a unit test for the stuff you use, actually.
That's sad.
Yeah, that's really sad. And I mean, obviously, if you can use some general tooling, sure, do that. But I mean, it's not always possible.
No, it's not. So, and when it's not possible, write your own algorithm.
Yeah.
So
Usually, there's something there. But
the algorithms, you know, you can go and look at Marshall's implementation of an algorithm and just pull it on in.
Or my talk from last year, how to write your own
Or how to write your own
Ah,
algorithms.
nice.
Yeah.
Thank
so,
you.
yeah, that would be better because you're not going to use all the algorithms. You're going to have some subset that you'll use, but use something that's already implemented.
Yeah.
I'm here all day.
So RTTI and exceptions, where
Yeah.
do they fit in this world?
Return both RTTI and exceptions off immediately. They don't exist.
Okay, could you back to slide send a message just before state machine diagram? So I'd like to ask type of state machine. Type of send a message. Just before.
There?
No. Just maybe 2 or 3. Back to.
No, I'm at the beginning.
So I mean, send a message to some command. So command array to you introduce some type. Maybe 2 or 3 slides back. That.
This?
Yeah.
Yeah.
The send message. What is the type of send message? So this you introduce 3 structures.
Yes.
They have different types. The send message type is template or something type erased.
No. Okay. Good question. So it's send message is actually a templated function,
Okay.
and I've given a variety of different talks in the past that talk about serialization techniques using structs and things like this with the send message. You can find them like CPP now. There is a talk on fusion where I talk about this technique. There's also a talk on modern techniques, which is a 3-hour talk where I talk about this technique. But you only have to write the serializers one time.
Okay.
And I don't mean like one time per message type, but per atom type. So
the follow-up question. So if the send message, maybe send message sending a message immediately, but if we need to enqueue the message, some container, if that works well.
oh yeah, so how to enqueue these and,
Yes,
hold on to them?
heterogeneous.
Yeah, you have to use type erasure
Okay.
and then pull it back out.
So, yeah, I have one idea. So you introduce a boost SML. Perhaps the deferring event could help.
So
To
yeah,
send a
so you'd have to have an any type thing with that.
The defer message is not invoke message immediately.
Right.
So instead of send a message, you can write defer.
Yeah, so we don't. So how we implement this is we actually don't defer the message. We send the message, and it goes through serialization.
Okay.
And there's some number of bits that are waiting on probably a DMA area for them to get sent out to the device. So we don't actually queue up
Yes.
type erase types. We actually, at that moment when it gets called, do the serialization so it's ready to go out. And they're just sitting inside of a DMA buffer somewhere.
Okay. Thank you.
All right. Looks like we're done.